We're going to talk about climate change today. And climate change is such a big subject that I have hundreds of slides on it. Anyway, so we're going to do this as fast as possible, hopefully, but also covering all the basics. Now, in your textbook, there is a section on climate change, but we're going to be discussing more than what's in that textbook. So let's get started. So we're going to be looking at climate change around the world. And one of the things is that people still would like to not believe that climate change is happening. And in 2006, Al Gore produced a movie called The Inconvenient Truth. And yet there are still many people who would rather have a reassuring lie. But over the years since then, climate change has started making itself very evident with the fires in California and across the West, with the hotter days, the loss of sea ice, and the rising tides and strange storms. So, anyway, climate change is here. So, it's not something that's in the future anymore, it's part of your life. Now, many people see climate change as one of the greatest challenges to humanity. Um, and it's a security risk for military people. I mean, when ships can't get into naval bases, um, when people are having to change countries because their own land is no longer can support life. What happens is that we have diseases that will be increasing, those especially related to wetlands like mosquitoes, malaria. Um, it's a food security issue because certain crops will no longer be able to grow in certain areas. And all over the world, farmers are having to adjust their schedules, adjust their crops. And in many cases, there isn't enough water. Anyway, so it's something that's already happening, and it's something that brings grave threats actually to life as we know it. All right, so let's go look at this. So, for some definitions, of course, climate is different than weather. Weather is something that happens on a day to day level. Climate refers to long term patterns. So, the idea is that weather, you might have a snowstorm and say, oh, climate change isn't real because we had a snowstorm. But we're still going to have snowstorms. We're going to have strange weather still. But in general, many parts of the world are getting hotter and hotter, almost all parts, and many parts of the world are already beginning to see a lack of rainfall. And so temperature and rainfall, those are what define a climate, and that is changing. So these are just showing some climate um, of the world, how they're defined. And so anyway, where we live, we are in this light blue area here. We are in a humid continental climate. Now, what is happening is that the orange part there, the humid subtropical climate, is moving upward some. Okay, so for us, that division across the United States, the southern heat is moving north, and in other places um, that were dry, they're now getting drier, so more like deserts. So you have different types of deserts, and so things are changing. Now, the world is changing, and the reason for this is what's called global warming, which is due to the greenhouse effect. So, our planet has been, over the last 50 years, across the whole planet, the temperature has warmed 0.8 degrees Celsius, which is around 1.4 degrees Fahrenheit. And that doesn't sound like a lot, but think of it this way. If somebody asked you for $1, you could say maybe yes, you probably got $1. But what if everybody on the planet asked you for $1? Suddenly that's a big issue. Well, the idea is that every atom on the planet basically is moving a little faster. Okay, the whole planet has warmed up, and that is a huge amount of energy. And that energy can change the climate, okay, and bring about differences in storms and melting ice and fires. Um, it doesn't take many degrees to change the world into an ice age. Okay, so 4 degrees colder or so, and you start looking towards an ice age. 4 degrees hotter, and we are looking at a very changed world in the other direction. More deserts, more extremes of weather because we have so much energy. Anyway, so let's go look at the greenhouse effect. And here is a great chart over here on the right. And one of the reasons this is great is because it has all these wonderful institutions that are involved in this chart. So this is comparing NASA data, the National Oceanic and Atmospheric Association, so those are two American groups, the Hadley Center, that's Europe, the Japanese Meteorological Agency, so that's Asian. And so now you can see that all of these are in agreement. As you look at the temperatures from the 1800s and then through the 1900s and on to the 2000s, you can see that it is climbing upwards. And so, yes, temperatures especially have been climbing in these last 20 years. And it's definitely good evidence that temperatures are increasing. And so when you're looking at climate data, you want to see who is producing the data. And you want to go, hope that you use the best data possible. All right, so what is the greenhouse effect? The greenhouse effect is the idea that, let's go back to a greenhouse. A greenhouse has glass windows, and the idea is that visible light can go through the glass windows. So visible light from the sun goes through the glass windows. It hits the objects inside, the plants, the furniture, the floor, and those objects warm up. Now, when objects warm up, they produce what's called infrared radiation. And so the visible light came in, but now there's infrared radiation, which, as we've discussed in class, is a longer wavelength radiation. And the thing is, the longer wavelength can't get through the glass, so it remains trapped inside the building. And because of this, the greenhouse warms up. Okay, now, when we're going to talk about our planet Earth, of course, our Earth isn't covered with glass, but it is covered with gas, which serves the same function. Okay, so visible light in, infrared radiation trapped. All right, so visible light has a smaller wavelength than infrared. And therefore, visible light has greater energy too. Now, this is the same thing that happens in a car that's sitting in the sun, which is why you're not supposed to leave your pet or your child in the car. Even though the outside temperatures you may think are not killer, once you start leaving it in the sun, then as the car heats up, from sunlight coming onto the roof, but also in through the windows, that heat energy is trapped inside the car. That's why you're supposed to at least lower the windows so that infrared energy can get out. But basically, you don't want to leave your animal in the car. Okay, now for the planet Earth, as I said, we don't have glass around us, but what we have is gas. And the gas around the planet does the same sort of thing. It shelters us from some types of radiation, but it traps infrared radiation. So there's gas, which includes water molecules and carbon dioxide, and those are all good at trapping infrared radiation. So terrestrial infrared radiation is produced after the sun has heated the Earth, and so all the objects on Earth are giving off infrared radiation, and then that can get trapped around our planet. And the more of these greenhouse gases there are, then the greater the ability to trap infrared radiation. So some infrared radiation is absorbed by the gases in the atmosphere that keeps our planet warm. Now, if we didn't have a greenhouse effect, then the Earth would be very cold. The average temperature would be around minus 18 degrees Celsius, which is 0 degrees Fahrenheit. So it's important that we have the gases that help trap radiation. It's just, you always want to balance, right? You don't want too much of a good thing. And that's what we've been doing. Okay, now there's a video which you need to watch, which is about how greenhouse gases actually work. So we're not going to watch it now, but there's a link in the chapter module, or you can copy this link. And so anyway, so go watch this video because it does talk about why gases absorb infrared energy and which ones absorb. And Henry right here, he does a wonderful bunch of videos called Minute Physics and Minute Earth. So if you're interested in science, he's got great short videos that are only a few minutes long. So like this one's 3 minutes long, and very well done. Okay, so solar radiation or visible light hits the planet Earth. The planet Earth radiates infrared radiation, and then the planet, gases trap that, and the planet stays warm. Now, so visible here, infrared here. Now, as I said, all things on the planet Earth pretty much give off infrared radiation. And to give off visible light, they have to be over 525 degrees Celsius, which is very hot. So here we've looked at this in class before, is a street scene showing how everything in here is giving off infrared radiation. The cars sitting in the sun are brightly colored in pinks and reds. Their temperatures in the 30s degrees Celsius. The trees are blue. They are also giving off infrared radiation. They're in the 20s. So everything is giving off radiation, including the people over here, right? Okay, so the greenhouse gases trap heat energy, and people started measuring carbon dioxide ratios in the 1960s. And when they did, they also noticed the connection to the temperature increasing. So the orangey red line here is the carbon dioxide ratio that was measured after the 1960s. And these have been consistently measured across the world, but Mauna Loa is where they started out in Hawaii. It's where these measurements were first taken. And then what happened was people went back and looked at ice core data, which contains bubbles that contain carbon dioxide. And so they've also put in ice core data to continue the line of the carbon dioxide. And you can see the temperature data that's been figured out over the years because people have been taking temperature for a long time. And you can see how they track upwards. More carbon dioxide, more heat trapped, higher temperatures. So Carbon dioxide level increases, so does the trapped heat, and our Earth warms up. Now, we have reached, in April, we were at 421 parts per million. So that's one of the ways carbon dioxide is measured. There isn't really a lot of carbon dioxide in the air. You don't need a lot to trap a lot of infrared energy. So parts per million, ppm, is saying that there are only 421 molecules of carbon dioxide in a million molecules of air. So it doesn't sound like a lot, but it's enough. And back in the 1960s, the level was around 320. The year you were born, maybe 2000, the level was around 390. And now the level is 420. So it's been increasing rapidly since you were born. And if we go back to this chart, you can see that the level used to be down in the 200s, okay, in the 1800s. So humans have been increasing the level as we drive more cars and have more factories and have more people. Okay, so which gases are we concerned about? You've probably heard mostly of carbon dioxide, and that is certainly one of the ones that we are most alarmed about. However, equally alarming pretty much is methane, so CH4. And that also traps heat energy. In fact, it traps it even better than carbon dioxide by quite a bit. But the thing is that carbon dioxide can last in the atmosphere for hundreds of thousands of years. And methane has a shorter lifetime. It eventually gets reabsorbed in different ways. So anyway, so the methane will only last maybe 30 years, but carbon dioxide lasts a really long time. So nitrous oxide that gets produced in car engines and incomplete combustion, that's also a problem. Ozone also can get produced in cities and again can be produced in car exhaust. And then CFCs are chlorofluorocarbons. And strangely enough, those are also one of our most dangerous gases for the climate change. And you may think CFCs were banned, and they were. But what happened is that we still have a lot of them. They're in storage, and they're not carefully stored in some places. And so that gas could be released. There also is the problem that things that replaced CFCs in air conditioners and refrigerators and things like that, those replacement gases turned out to be just as bad as CFCs for the as a climate change gas. So CFCs use mostly connected with the ozone layer. They destroy the ozone layer. The replacement gases don't destroy the ozone layer, but they are heat trapping gases, greenhouse gases. And by the way, this ozone that's being produced here isn't the ozone high up in the atmosphere that's naturally produced that protects our planet. It just hangs around our cities and creates smog and traps heat. Okay, so anyway, so those are the big ones, and we're mostly going to be looking at carbon dioxide and methane. Now, as I was saying, one of the problems is that carbon dioxide molecules, once they get into the air, they might just hang around for 100,000 years. And so you're saying, well, trees absorb them. That's right. Trees do absorb them, but the problem is we don't have enough trees now to handle the number of carbon dioxide molecules that are being put out into the air. So we don't have enough trees. Can we just add more trees? Well, we can add more trees. That's one of the ways that climate change may eventually be defeated. But we have to make sure that the trees live long enough, because if if they just die and then rot, that carbon gets released again. They have to have undisturbed root systems that lock the carbon underground. And so we need lots and lots of more trees, but also we need to not just degrade the trees and wetlands that we already have. Wetlands are also really big at pulling in carbon dioxide. And seagrass. So things that we don't think about in the ocean. The seagrass is also really important. So anyway, so the problem is that adding carbon dioxide to the air is easy. Just burn some gas. Celine, removing it is actually hard. So how are we going to remove all the carbon dioxide that we've already put into the air? Now, there will be another part of this talk called, which is about geoengineering and how we can fix the planet that we broke. Okay, so first we're going to talk about consequences, then we're going to go back and talk about how to fix it. Okay, so when you look at the greenhouse gas emissions, a lot of it comes from industry, transport, so when you drive your car or transport goods, okay, electrical production, so burning fossil fuels to make electricity and heat. But a surprising amount comes from the agriculture section. That's about 14 to 15%. We're just going to go over that briefly because amazingly, almost 10% just comes from cattle. And they produce a lot of methane. And even cow burps are on here because they can produce almost 4% of all the gases being produced in our planet. So, so this is something that we can take care of a little bit. And so some people are trying to figure out what they can do with cow guts to change their diet and see if they can reduce greenhouse gas emissions. So they found that making cows eat garlic can reduce methane levels. But basically, if we eat less beef, that will help our planet a great deal. Our diet is actually one of part of the problem. Okay, so anyway, chicken, fish, those all have fewer greenhouse gas connections. And then there's the Impossible Burger, which is hugely less of a strain on our planet, and tastes great. So anyway, so eating less beef is actually one of the things you can do. So if you can eat less beef once a week, you're actually helping the planet. So choose the chicken. Okay, or vegetarian. Okay. So anyway, so just something that it's not just carbon dioxide, but many gases contributing. Okay, now carbon dioxide is the main one though, and so we're going to look at here. This is a chart showing carbon dioxide levels way back in the past, so hundreds of thousands of years ago, that have been able to be found trapped as bubbles in ice or in volcanic rock. And so anyway, so when we look back, we have not gone higher than this level, about 300 parts per million, for 650,000 years. So our planet is a different place than it used to be before that. And right now we seem to be rapidly returning it to a place where we have very high carbon dioxide levels. So you can see how in the 1950s we really shot up since then. This one only goes to 2013, but I already told you we are now at 420. Now, the thing is, if we go back to when the carbon dioxide level was this high, that was about 3 to 5 million years ago. The temperature was 2 to 3 degrees warmer. The sea level was 10 to 20 meters higher, so that's like 60 feet higher. So yes, so the world has experienced high carbon dioxide levels before, but it also was a different world. The planet will survive this incident. It's kind of like, will the humans survive and the other animals, and will they be enjoying it? So we have really been shooting up lately. Again, this is that temperature chart that we looked at. And this last decade has been the warmest on record. And in fact, the last 20 years have been the warmest on record in recent history. Now, if we go back millions and millions and millions of years ago, then there were times when the carbon dioxide level was much higher than it is now. We are actually at a very low carbon dioxide level. However, the planet always wasn't a pleasant place when there were high carbon dioxide levels, and often it led to mass extinctions. So that's part of the problem. We are returning ourselves to a time when the Earth was warmer, it was swampy, it was sometimes free of ice, and that's because the carbon dioxide that we're burning, that was often laid down as coal beds and as in natural gas formations. That was laid down millions and millions of years ago, and what we're doing is releasing it. So we are basically returning ourselves to, well, the time of the dinosaurs. They were going through a high carbon dioxide level situation. And because there was so much more water covering the continents, then what we had was a lot of swamps and wetlands. And that's, of course, where a lot of coal was laid down as plants fell into the swamp. And so as we burn fossil fuels, we are releasing that carbon dioxide again. Now, the thing is that the Earth was not a very nice place in many ways. There were lots of areas that were huge deserts if you were along the equator, and a lot of dinosaurs didn't go there, okay? But it was much more tropical, places like up where we live. So yes, so the thing is we are kind of returning to those times. So climate change is not really a threat to the planet itself. It's just a threat to the creatures who inhabit it and the creatures that have been living with nice, cool temperatures for, well, millions of years. Okay, so it's only a threat to the Earth as we know it, and the people and the plants and the animals on the planet. Okay, so temperatures have been increasing, and when you look at the evidence, it's because we've been releasing so much greenhouse gases. The idea is that by the year 2100, a lot of predictions go out to 2100, the temperature increase will be anywhere from 1.4 to 5.8 degrees Celsius. And basically, you can kind of double that to get the idea of how much hotter that would be in Fahrenheit. Now, that doesn't mean it's going to stop at 2100. The increase will perhaps keep going up if we don't get a handle on this. And so since you guys are around 20 now, in 2020, that means by the time you're 100, you'll be able to see, were we able to succeed or were we not? Now, climate change doesn't change equally around the planet. The temperature difference in the northern hemisphere and in the far north, in the Arctic, that's much greater than the temperature difference in many other places. And so we're going to talk about why the Arctic is heating up greater. So they're already experiencing a 2 degrees Celsius change, which is about 3.5 degrees Fahrenheit. And so if you've heard stories about Canada having temperatures in the hundreds this summer, well, that's because we have heated up the northern lands. And there's another video here which you might want to watch as these temperatures increase. And of course, red is an increase, blue is decrease. There isn't going to be much blue, but there is a lot of red at the end. Okay, now across the United States, 2016 was the hottest year on record. But 2019, 2020, and 2021 have broken many temperatures records. And so yes, so definitely the United States, along with the rest of the world, is heating up. Now, actually, in many parts of the world, it's worse than in the United States. You probably heard of outrageously high temperatures in places like India. Um, but all across the world, the temperatures are increasing. So the Earth's average temperature has been going up. So the blues here are in the 1800s. And then you go up to the 1900s in the turquoisey colors. And then you get to the years 2000 in the green. And then we're going up to the red and the darker colors. Those are these last few years, the ones you've been living in. And you can see that the hottest temperatures um, have been going up around the whole planet. Okay, here's another cool graphic to try and understand this. This is plotting um, 40 some years of data, about 40 years of data, with the warmest month ranked 1. So, like, there's a 1 over here, and that is 2020. And then the coldest month would be, let's see, I guess they do have 41, is the dark blue. And that what you can see is that before the year 2000, there was quite a bit of what would be ranked now as colder months. But you can see how from 2000 and up, we have nearly all the high temperature data. And we're having, of course, record temperatures this year also. So when they have to wait a while to get all the data in. But yeah, this keeps getting updated. 2016, you can see right now it's got 1, 2, 3, 4, 5, 6 records for hottest month. And that was actually January, February, and March, and September, October, November. And you can see 2017 had the hottest December, because it's not just the summers getting hotter, it's the winters getting hotter. And that, in fact, is driving some of the most changes in plant movement, because plants that can't have their roots freeze are now being able to move further north because the winters are more mild. And you can see 2020 had 3 records already. So anyway, so I need to find another update to keep updating this version. Okay, but I hope it gives you pause here that yes, your 20 years of life have lived in warmer days. So when your folks tell you it used to be colder, they were right. Okay, it is warmer now. Okay, so how do extreme temperatures affect us? Well, it can get too hot to work outside. And so this is happening around the world. People die if they just keep working, especially outside in farming and construction. Um, it's just exhausting and painful to try to work in really high temperatures, and dangerous. It gets too hot for vacation spots. So countries and cities that used to rely on tourists, when it gets too hot, nobody wants to go there, right? So you probably said it yourself, oh, I don't want to go to Washington, D.C. in July. It's just going to be too hot. Too hot for crops. Um, Hotter weather leads to more evaporation. So you've got the problem of large amounts of heat. Plants have to evaporate um, uh, through their leaves, and there's not as much moisture in the ground. It's not available. Gets too hot for airplanes to take off. This has already happened where airports, when the heat affects the air by making it less dense, an airplane can't take off necessarily. It can't hold the same amount of weight as it used to because the air is less dense. And too hot to live. Your body needs to cool off. Your body needs to stay around 100 degrees Fahrenheit. If it's 120 degrees Fahrenheit outside and it doesn't cool off during the night, then what happens is people die. Their bodies cannot live at such extreme temperatures. Um, so anyway, so yes, so it is a problem that we have more extreme temperatures than we've ever had in the history of the human race, pretty much. All right, so hundreds and hundreds of thousands of years. Okay, now, you've probably heard the quote about 97% of all scientists agree about climate change. Well, that's not quite the right quote. It's publishing climate scientists. I mean, there are a lot of scientists who really don't have enough information to make a good judgment on this. So you can't say every scientist. It's the climate scientists, the one who actually are doing work in the field. They're in agreement. And it's even higher than this. They definitely see the relationship between climate and greenhouse gases, and human beings putting out the greenhouse gas. There's nothing else happening on the planet that is creating these greenhouse gases, just humans. Now, so what's going to happen in the future? Well, there are lots of models, and so we will be looking at some of the predictions about the future. But basically, if we stop making carbon dioxide today, pretty much, then this would kind of be what happens with temperatures. So the temperature would not climb up too much more. It would climb up a little bit more. But of course, we're not going to stop making greenhouse gases today. So various models are what would happen. Now, if we just continue the way we are without substituting for fossil fuels, that red line is where we could be. So we would be in temperatures that might be 4 degrees higher by 2100. But various scenarios might give us temperatures differently. Okay. So anyway, so yeah, so it depends on us as people taking the responsibility and changing the future. And if we want to keep things like coral reefs and ice in the ocean and glaciers on the Alps, then we have a lot of choices that need to be made. Okay, so anyway, we'll be looking at melting of glaciers. We'll be looking at increases in extreme weather. We'll be looking at warmer uh, temperatures at higher altitudes and what's that happening. And we'll be looking at the ocean, and we'll be looking at a number of things. So we're going to take a break now and then start with the warming the northern oceans. Okay, so part one is over.